Hello and welcome to this video tutorial. My name is Mühlhaus. I'm the software architect of this product, and I'm going first to show you a short introduction with a few slides, and then we jump right into the software to see things in action. To understand why it makes sense to design customized inductors, let's have a look at this inductance and Q factor plot over frequency. It's the exact same inductor value, but you can see that the performance is very different at different frequencies. So we have the same value but different performance, and that's why libraries which are easily available in the PDK typically don't provide the best inductor for your needs. These library inductors, they have one value at some frequency, but typically they don't have the value that you need at the frequency where you want to use that inductor. And because inductors are physically large devices taking a lot of chip space, we want to make sure that this chip space is used in the best possible way and the inductor performs as good as possible for your needs. So, RFIC Inductor Toolkit for ADS does the work for you. You just need your specifications, and Inductor Toolkit will design that inductor for you. It synthesizes EM-accurate inductors for a given target frequency with the best possible Q factor for the given geometry limitations. It also automatically creates EM electrical models for the optimized geometry, so you get the proper SPICE equivalent circuit models. You can choose from different layout options, single-ended or differential with or without center tap. We'll see that in the next slide. For the inductor shapes, we have different choices. We have symmetric octagon, which typically has higher Q factor than the symmetric square, but you can choose from these two. We also have stacked metal, we have patterned ground shield, and we also have asymmetric square inductor with all the different field line orientations. Okay, let's get started with a live demonstration. After installing Inductor Toolkit into your project, which is just done as an ADS PDK, so that's very simple, you will see this additional menu, Inductor Toolkit, and the different steps that you need to take are numbered. We start with number 1, set layout option, and choose the differential center tab octagon, so the symmetric octagon. Now, second step after choosing the layout is we need to set the target inductance. What inductance do we want to design? In our case, we want to design an inductor with 2.5 nanohenry. You also see the geometry space where we search in from 1 to 5 turns, 5 to 30 micron widths. And we have a maximum outer diameter for the inductor of 600 micron. And that's to limit the physical size of the inductor, because otherwise you would end up with physically large inductors which are typically performing very well, but they are physically large and cost a lot of chip space. Okay, we save this, close the window, and proceed to step 3, which is sweep parameter combinations. I forgot to show you something. Here you see how many inductors were synthesized which meet the specification. So in this case, there are 10 different inductors which conform with these specifications and all give you 2.5 nanohenry. And now, with this step, we want to find which of these is performing best. So it's running all this through Momentum. Actually, in this case, we are using cached EM data from Momentum. So this is very fast. Otherwise, it would take a minute or two to get to this point. This is the overview window where you can see the synthesized inductor. You see all the different inductors have the same low frequency value, but they differ in self-resonance frequency, and they differ in the frequency of maximum Q factor. And now our target was 2.5, that's done, but what is our frequency of interest? and I can set the frequency of interest here. And as I move the slider to different frequencies, you see that different curves are highlighted, and the software automatically finds the inductor that performs best at this frequency. So if we go to a high frequency like 10 gigahertz, you see the best inductor has changed. And here on the right side, you see the differential Q factor at this frequency of interest. You see the inductance at this frequency. It changes with frequency, as you can see, as we get closer to the self-resonance frequency. It's no longer the DC inductance. And you see the physical parameters, number of turns, outer diameter, width and spacing for this inductor. In our case, we wanted 5.8 gigahertz. So we just enter 5.8 and find one inductor which is performing best. Now we need to fine-tune this inductor to this frequency to account for the differences in inductance over frequency. That's very simple and automated. We just do step 4, fine-tune inductance value. Okay, and this gives us our final inductor. So you see we can have a differential Q of 11 at 5.8 gigahertz. The inductance that we've synthesized is 2.57 nanohenry. We have 4 ohms DC resistance, and the physical parameters: 2 turns, 401 micron outer diameter at 25 micron line width. And that's somewhere in between the range of 5 to 30 that we had specified. So it's not the smallest or the widest inductor trace. It's something in the middle, and that's what this automation was about, to find the best performing layout for your needs. And it has also tried other number of turns, etc., and found that this is the best within this whole geometry range. Okay, we could now proceed and directly create a layout cell, but what we can do as an optional step, we can create an equivalent circuit model for your inductor. This will result in an SCS file which you can use in Spectre, or you could just look at the equivalent circuit model's values to get a physical understanding what this inductor is about. And in my work on inductor EM simulation, I found a lot of users who are not so happy with black box models like S parameters or broadband splice models, and really want to see a physical model that has series inductance and shunt capacitance and this kind of elements. And so this is what happens at this moment, and it's giving a very nice fit already. Just need to re-simulate this, and you see we have a series inductance where the red curve is the underlying EM data for the inductor, and the blue curve is what this electrical model gives us, the equivalent circuit model. Perfect match in inductance. We also have a perfect match in Q factor. We have a very, very good match in the other circuit parameters like the series resistance. We have a very good match in the shunt capacitance to the substrate, and also in the shunt resistance to the substrate, and of course in the S parameters. So what does that model look like? We'll see that in a second. Let's now create our final cell, which is the end result of everything. So here's our equivalent circuit model with the values and the underlying circuit model. Here's the S parameter result, which you can use in simulation if you like. And here's the layout. This is the DRC-clean layout cell for this best performing inductor for 2.5 nanohenry at 5.8 gigahertz. What we also have on disk is the Spectre model that was created from the equivalent circuit model. So you can use this in Spectre. This file contains the equivalent circuit model for your optimized inductor. So that's the second model which you could use besides the S parameters. Okay, let's summarize what we've seen. We've looked at RFIC Inductor Toolkit for ADS. And we started from your input, your required inductance and the target frequency. You start with the electrical parameters. Also, you had a chance to specify certain geometry limits, which are limited by your technology or just by the available chip space. And then Inductor Toolkit has automatically found the best possible layout within this geometry range. So it has synthesized your inductor based on your electrical parameters, and you get the DRC-clean layout for this best possible inductor. You also get EM-accurate simulation results as parameters, and you also get an equivalent circuit model, so a real physical model, and that's created also as a Spectre SCS file. So if you want to use this in Cadence, you can just take the DRC-clean layout and the SCS model to the Cadence world now. And what you have not seen is the great degree of automation and expert level knowledge that's built into RFIC Inductor Toolkit. So for example, for this circuit model, it's all there, it's automatically set up, all the goals are automatically set up. It's set up so that it doesn't try to optimize for something that's outside your frequency range of interest. So it's all highly automated to make it very easy for you, so that you just need electrical parameters, and Inductor Toolkit finds the best performing inductor for you completely automatically. That ends our tour. Thank you very much for your interest, and I'd like to hear from you. And if you're interested in a demo, we have demo versions for many different technologies and foundries.